Okay, let's transition mentally to the next part. This is going to be last lecture followed by the last practical, which should take up any remaining time that we have. Again, just a reminder, afterwards we're going to go to happy hour at the
union. Yeah, happy hour.
You can drink at the union?
Yeah, they're going to bar and stuff.
How to move this. All right. So yeah, in case you'd like to join us, and then we're going to get dinner at
Bel Air.
Bel Air.
Downer. Yep. Which is only about 2 minutes away from here.
Yeah. So if you want to skip happy hour, go rest a little bit, come back for dinner. Free to do so.
Yeah, if you want to go and you didn't RSVP, just come and talk to me or Mai after class, just so we can get an estimate of how many people are going and we can put in our names at the restaurant.
Okay. Ready? This is what we trained for, right? All right. Here we go. MVPA, what can I say about it? First thing you should know is there's some debate over what the acronym means. Some people say multi-voxel pattern analysis. Some people say multivariate pattern analysis. Doesn't really matter. Just say MVPA. They refer to the same thing. Now, why does MVPA exist? Well, machine learning techniques have been floating around for a while. But back in 2001, there was a researcher named James Haxby, who was working at NIH at the time, who was examining responses in this area, this ventral area of the brain. We're looking from the bottom up. This is front, this is back. Looking within the fusiform face area, or FFA. So both that and the parahippocampic place area had been shown to be involved in processing faces, objects, and so on. Now, what Haxby was interested in, initially, this is his classic 2001 paper, was looking at categories such as faces, and he noticed that if you looked at if you divided your runs into two sets, say even runs and odd runs, and then you looked at the correlation between the activation for faces for the even runs and the odd runs, there's a very high correlation between them, 0.81. But if you looked at between categories, and it's the same story over here for houses. If you looked at the correlation between the categories, there's actually a negative relationship between them. And you could extend this to many, many different categories of objects. So chairs, shoes. In the data set, in one of the data sets we'll be looking at this afternoon, we have his original data, and we'll be looking at these original labels that he looked at. Now, based on this, this was the foundation of a new technique called multi-voxel pattern analysis. Because even though in some of these regions, let's say for chairs, shoes, houses, you would find, if you try to do a contrast between them, sometimes you would find no difference between them. Right? So it's like a wash between the response for chairs and the response for shoes. But the magnitude of the response, and this was the key insight, doesn't convey all the possible information you find in these data sets. And some people think that it's a shame that we collect so many thousands of voxels, but we tend to boil them all down to a single number within these very large areas, which is what we've been doing so far. It's appropriate. There's nothing wrong with it. But there's more information to be gained there. And if we look at not just the absolute magnitude, but the pattern of magnitude across the entire region, can we categorize that pattern of activation as belonging to chairs, or to shoes, or to faces, or to houses? That's the whole concept behind multi-voxel pattern analysis. We're no longer looking at just magnitude, but patterns of magnitude, using entire sets of voxels. Let's see. This is basically the same thing, looking at a different, cats are fish. We'll be looking at those as well. This is just another way to look at it. So you do find very high within category correlations, but not so much between categories. And you can extend this to a bunch of different scenarios. There's a nice paper by Kamitani, 2006, in Nature Neuroscience, where that group looked at whether different orientations of stimuli can be decoded in different parts of the cortex. So what you'll see here, so they looked at different subsets of visual cortex, and this is a pretty typical accuracy plot that you'll see. Okay, we'll be doing something similar. So if you can see here, there's a dot, 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 dot. This represents what the chance threshold would be. So what you'd be doing, let's say you had only two categories you were distinguishing between. And you're trying to train a classifier to distinguish what pattern belongs to category 1 or category 2. So chance level, if you're testing this on some new data it hasn't seen before, chance is going to be 50%. If you have multiple categories it's distinguishing between, let's say in this case, let's say they had 8 categories, I believe, then chance would be 12.5%. Because just by chance, 1 out of 8 guesses would be correct. What you're looking for, what they look for in these plots to test whether the classifier did a good job, is if it's significantly different from that chance level. Right? You can look at this across multiple different regions and training it in different ways. Now, I talked about that leave one subject out cross-validation before. You can also apply cross-validation to MVPA. So in that case, you have, let's say you had 10 runs of data. In Haxby, they had 12. Let's say you have 10 runs of data. You would take 1 run of data, and you would leave that one out. You would train your classifier on the remaining 9 runs of data, and then you would tell your classifier, here's this new run of data that you have not seen before. Can you determine whether this was condition A, condition B, condition C, or so on? You test that through all your iterations, and then you can plot these error bars to see how much variation there was in that accuracy estimate. So overall, that pattern was it a pretty good classification pattern, and which region of the brain was responsible for it. So why is this useful? Now, like I said, if we go back to, say, some of our Z maps, some of these areas that are brighter, those tend to reflect where the magnitude is greatest. These other ones, they may not pass the threshold, but they can still contain useful information. That's probably the case that there's some, in a certain region, let's say that this was all related to one functional region processing conflict or incongruency. It's entirely possible that doesn't mean that everything has to be really bright or really active to process congruency or conflict. It could be that there's something more complex going on where certain regions need to have more blood flow, more activity, other ones need to be more suppressed or inhibited in order to successfully do certain cognitive operations. Okay, so we'll be going over the basics of MVPA. We'll be applying something called support vector machines, or SVMs, to an example data set. And then the final exercise, which this is the first time I've done something like this, so you're the guinea pigs. We're going to be using Haxby's data set to basically start to finish doing the pre-processing, doing some of the checks, deciding as a group how we're going to create the ROI, and doing our analysis from there. To start out with, we'll be doing SVMs on a pretty simple data set, just because I know it's going to work on that, and it does all the basic principles of MVPA. So even if this crashes and burns and it's just a complete disaster, you'll still have enough training to understand how to use 3D SVM. So this is my insurance against. It might be really good, and people will be like on their desks and like Maybe it's probably somewhere in the middle between that and the giant dumpster fire. Okay, so let's talk about a couple different types of MVPA. Today we're only going to be focusing on one of these, which is support vector machine, but I want to speak to, I'll talk a little bit about another major one called the Searchlight algorithm. Now, what we do with this pattern analysis, you need to know the distinction between supervised learning versus unsupervised learning. So what we do with these classification algorithms is we use a procedure called supervised learning, which uses features to classify new data. These features can be anything, different dimensions. They could be things like, well, I have an example on the next slide actually, but in fMRI, the features that we use for classification are usually the both signal in voxels. And the more voxels you have, the more dimensions that you're using to classify. So if you imagine like a traditional axis, like a 2D space, and I had bold activity for voxel here, bold activity for voxel here, and I could see where different coordinates of, say, activity for voxel 1 versus voxel 2 are, and then try to distinguish between them. I have a better animation for that, so I should just move on to that. But let's start with a very common example, only 2 features. So this would be the simplest one because you need to discriminate between these 2 things. Let's say height and hair length. And we know, on average, males will be a little bit taller than females, and on average, at least in America, I guess, hair length is usually longer on females than males. On average. I mean, obviously, there are different variations because you could have a relatively short person with long hair. This is Sam Kinison, stand-up comic. You could have somebody who's very tall but with pretty short hair, right? Anybody know who that is? Tell this one. She's like 6'4" or something. What? She's gigantic. Yeah. It's something like, maybe I'm exaggerating, but she's probably taller than that. What's that? She's 5'11"?
That's what the internet says.
Yeah, but whatever. She looks like she's 6'4". She's got a long neck. In heels, she's 6'1".
Big heels.
The common 5-inch heels. Okay. I'm going to edit that out. Because I was away. In any case, doesn't matter. So let's say, so we have these 2 features. Let's say we z-score them or something. We put them on some kind of common metric. And we have height on one dimension. We have hair length on the other dimension. Okay? So most males would have relatively tall but relatively short hair length, and most females would have be relatively shorter but longer hair length. So this is just some sample data that we collect, and if we wanted to, we could try to divide these 2 groups to create 2 separate categories. And the way we do this is with a mathematical feature called a hyperplane. So we use this to, in this case, bisect these 2 groups, and it has a dimension of p minus 1. So p meaning the total number of dimensions of features. So it's one-dimensional, it's just a single line. If I had a 3rd dimension, if I added on something like shoe size, some of these things are correlated, so it's not a perfect example, but say I had a 3rd dimension, which was shoe size, something like that. The hyperplane, how many dimensions would that have? 2, right? So 3 features, the hyperplane is 1 less than that. So imagine a 3rd feature coming out in the z direction towards you, that's shoe size, and now the hyperplane is going to be a 2-dimensional plane, like a ramp, that's going to be at a certain angle, that's going to try to classify things in 3 dimensions. Now, beyond 3 dimensions, it's very hard to visualize what exactly that looks like. And in the case of fMRI data, where we could have as many features as we have voxels, it becomes extremely complicated to keep in mind.
Are we always dividing into two groups?
No. This is just kind of a toy example. This is with two features, and I'm trying to use it to classify two groups.
But then this hyperplane of a subspace with a dimension p minus 1 would still hold, even if you were classifying into more than two groups?
I don't think so. If you were trying to classify more than two groups, I don't think you could, because this will only separate it into two separate areas. If you had, no, I'm not going to follow that train of thought. Okay, so how do we actually determine what hyperplane best separates this data? So all three of these hypothetical lines could separate these into two groups. They do the job accurately. But obviously they're not all the same. They all have very, very different slopes. So how do we choose which one of these is the best fit or the best separation? It's a similar idea if you have ever done, well, everybody here's done linear regression, but we try to find the best fitting line. And there are multiple lines we could possibly fit to the data, but our criteria in that case is trying to minimize the squared distance from that to each of the data points. So we're looking for a similar criteria that we can use to do that. And in this case, we do something called maximal margin classifiers. So this black line is the hyperplane, and it's trying to maximize the distance between the fringe data points for this group here and the outlier data points for this other group here. So that shaded plane is the margin. It's trying to maximize that distance. The data points that are on that edge of the margin, we call those support vectors, and hence support vector machine. Did I get that right?
Yeah.
Okay. I forgot what the algorithm was. Support vector machine.
That's just doing it for effect.
No. Yeah, it was pretty good, but no. That was because I forgot. Yeah. Okay, so going back to this, so that's what we use to try to classify the data that's given to it, right? And then if we get a new data point, let's say right here, and the hair length is a certain length and the height is a certain height, you know, let's say this person's standing behind a door, and I go, here are their metrics, height and hair length. Do you think that this is male or female? Right? According to the support vector machine, it's going to classify it as a male. But let's say I open the door, and lo and behold, it's actually a female. In that case, that is a miss. It's an inaccurate classification. If it was correct, it would be an accurate classification, and then we could build up an accuracy distribution. So the original data was used to train the classifier, and we held some data out. We tested it to see whether it actually correctly classified it, and then we can calculate the accuracy over time. So we can feed it a bunch of different things. This cross-validation technique is pretty common to try to get a good estimate of how accurate that particular classification was. If it does a really poor job, that can suggest a couple of things, but you know, the easiest thing to rule out are that these two features are not good classifiers. They may be unreliable for whatever reason. Excuse me. Now, we're dealing with these linear support vector machines. They're, you know, the easiest to use. Obviously, linear systems are very, very tractable and very computationally efficient, but they are not the only type of classifier that's out there. we're not going to use these, but you can use nonlinear hyperplanes. You can use very nonlinear hyperplanes that basically try to find islands or pockets within the feature space. But those are very complex, and they run into a higher risk of what's called overfitting. So you could have things that are actually, you could be using, you could make this so flexible that it does a great job for on the training data, but when it comes to the test data, it really just falls on its face. Okay, so some applications for fMRI data. Usually what you'll see with some of these classifiers is something called accuracy maps. So at each voxel, you can test what the accuracy is. You can compare that to a null distribution of what the accuracy should look like at chance, and then create these different weighted maps to see where and in what voxels it was most significant. Usually you see this using a Searchlight algorithm, which can go through the different predefined cluster sizes in the brain, and it goes systematically through each voxel with a certain radius, and it examines how well that voxel is at classifying something given its neighborhood. So build up maps like this. You can build whole brain maps. What's more common is for people to restrict their analysis to a single region of interest. But if you want to do a whole brain map like that, Searchlight algorithms are very, very useful. The paper you want to read if you want to look at a Searchlight algorithm is Krieges Kortz et al., 2006. And you build a Searchlight, or basically a bunch of neighboring voxels around a central voxel, and you place that at each voxel in the brain. So it goes through the entire brain. It creates this classification map at each voxel, and then you can overlay those and submit those to a group level analysis, assuming that these accuracy maps are normally distributed. If you do decide to go that route, my best recommendation is something called the Decoding Toolbox. It runs in MATLAB, and it's a very good introduction to the Searchlight algorithm. Not least because when you actually run the Searchlight algorithm, let's say you give it a certain radius, you give it a mask, it will show you in real time how it's classifying everything. So it steps through one voxel, another voxel, and it makes it very intuitive what's happening. And then you can create accuracy maps like this. It tells you the chance level, 12.5, because maybe there were 8 categories to discriminate between, and then you have a heat map for what the accuracy is. Okay. Unfortunately, we don't have MATLAB installed. We're not going to get to it today, but it is an option. And I found at least the tutorial for the Decoding Toolbox was very easy to walk through. So if you have access to MATLAB and you want to use Searchlight algorithms, I would start there. We don't have access to a Searchlight algorithm in AFNI. We have 3D SVM, that's slightly different. So, I'm sorry. Okay, oops, not so fast.
It's independent from SVM, right?
What is?
This
Yeah, that toolbox, you don't need I don't think so. I may be misremembering because I used it a couple years ago. But I don't think you need it. Yeah.
Is this used with when you're looking like global
Yeah.
application?
Mm-hmm.
Okay. Is he for like resting state as well or no?
I haven't seen it as much with resting
Yeah.
state. Yeah. Usually you'd want some kind of task so that you could discriminate between conditions. That's not to say you couldn't, like at a more abstract level, you couldn't feed in like say resting state maps from one subject population, another subject population. You give it a new resting state map, and you. This is why I love editing this stuff out. There's nothing wrong with your voice cracking, right? What was I saying? And then you could feed in a new resting state map. Yeah. I haven't done that, so I don't know. I couldn't direct you to a tool for doing that, but conceptually it should be similar to what we're doing here, just on another scale. So today we're going to be using the support vector machine instead, and we're going to be using 3D SVM to use it. Stephen LeConte was at the Michigan workshop about a month ago. I really liked his lecture. He had this whole thing about Kung Fu and how you like rotate it to separate these things. I could try to do that, but I'd screw it up, so I'm going to leave it to the pros. Okay, a few more words about MVPA design considerations if you want to apply this to a new experiment. The main thing for MVPA, and I was talking to Debbie about this actually during the break, is that you want to keep the pattern representations distinct as possible. You don't want to be introducing deconvolution if you can help it. What that means is you want to try to keep these trials as separate as possible so that the entire bold response can play out without any interference from another condition. Another consideration is that you don't want to smooth during pre-processing. Why might that be?
Because you have too much change factor.
Yeah, so you're going to be introducing, essentially, with smoothing before with task data, we're trying to bump up the signal, like the amplitude of the response. But here we're not as concerned about amplitude, we're concerned about what the actual pattern across the entire region looks like. And if we use smoothing, we're going to distort that. Okay. In this case, noise isn't, it's almost like we have a different concept of what noise is with MVPA. Noise for a typical task data set is too much variability. We don't like that. With MVPA, variability is the point. We want there to be enough variability to distinguish between one class and another. Most univariate principles apply. So for example, more trials, more time points is better, right? So there's nothing really changed there. But I've also read that it's unclear if higher spatial resolution is actually beneficial. The jury, as far as I know, is still out on it. I haven't kept that current with it. Maybe there's a new perspective on it, but from what I've seen, if you try to look at very, very fine resolution, say 1 by 1 by 1, do you get a gain above and beyond doing something like 3 by 3 by 3? It doesn't really seem to be the case. Now the trade-off between all of this is, yeah, you need more trials. More trials is always better. But if we have a design, like a slow event-related design, where there's enough time for the entire bold response to come back to baseline, that places a restriction now on the number of trials that you can have. It's a trade-off, and there's no easy way around it. As with resting state, head motion, as always, is a dangerous confound. This is one estimate that I saw a long time ago, which surprised me. Decoding accuracy seems to be correlated with head motion at negative 0.66, which is very, very large. So make sure your subject doesn't move. Also, block designs are recommended if possible. That's how Haxby did his particular analysis. I think it's what we'll be looking at in the sample data set as well. Okay. So we have a couple of different data sets. The first one is kind of a simple, safe data set we're all going to walk through together. It's from Brown University. There are 4 categories: faces, cars, shoes, houses. What is chance accuracy in this case? 25%. Very good. And what we're going to ask is, can we discriminate between these classes in the FFA? Ooh. The next Haxby paper is what we'll do after that. We incorporate everything that we've learned so far. But for now, let's take a look at this example data set. Let me just get to the same place. Okay. Okay, if you go into MVPA demo, does everybody see something like this? Yes? All right. This is single subject. All the pre-processing has been done for you. So you run 1 pre-proc, 2 pre-proc, and so on. Sorry, just give me 1 second here. Right. We also have 1D files telling us when the cars were appeared, faces, shoes, and houses. Those are the main things. We have a couple additional things like, which time points we're going to censor just based on, what they found during pre-processing. And I've included some scripts to walk you through sequentially what's done at each part. So you can follow along on your computer to look through these. You don't have to. You can just look up here. That's fine as well. I'm going to use the VI editor to look at 1_rundecon.sh. So first of all, we removed some stuff that might have been there from before. 3D deconvolve uses every preprocessed run, and in the modeling section, this is something new we haven't seen in 3D deconvolve before. Before we had stim times, right, for all of our onsets. Does anybody remember what stim times did? Remember I compared it to this other thing called stim files. What was unique about stim times?
Give it the time in seconds when the event came on.
Right, we gave it the time in seconds when the event came on. And what did it do?
Stim times is the thing that you're interested in. It's not.
Created the design.
Yeah, these are things that you're interested in, but it does one more thing. Convolves with the href, yes, or whatever basis function that you specify. Stim times IM stands for individually modulated or individual modulation, I forget. It's going to so with stim times without the IM, it's trying to find what is the average amount you need to modulate the href's amplitude by in order to fit it, as best we can. So it's basically being applied for every, like an average of all the trials. Stim times IM is doing it for every individual onset in this cars.blockout onsets. Okay. If you do beta series, you'd use stim times IM because it's looking at each trial individually. We can convolve it with a block of 9 seconds. That's how long they saw each of these stimuli for. So they see cars for a 9-second block. They see phases for a 9-second block. And we would know when they would see each of those based on the onsets file.
I'm sorry, can you say that one more time? What is stim times IM? I'm missed that.
Yeah. So it's going to be giving you an individual beta estimate for each instance of this condition. So let's say I had 8 trials of cars, right? So in other words, there were 8 blocks of 9 seconds where they saw cars. The reason this is important for MVPA is that we're trying to use each of those trials to build some representation of what it looks like in that particular trial.
Right.
We're not averaging across all of them. Yeah. What you'll see is we'll be stringing together each of the beta estimates for each individual trial when we're training our classifier. Yeah. So you can look at, say, the first 7 and then train it on number 8. Right? So if we look at that 8th trial, we know it's cars, the classifier doesn't. We give it to the classifier and say, was it cars or something else? Based on its beta map representation. And see how well it classifies.
So this is right. So this is a step 1 before you even do.
Yeah, this is
between the subjects out.
Yeah.
Got
This
it.
is necessary before we do any kind of classifying.
Right.
Yeah.
Okay.
So that would be a number of boxes by number of number of events matrix that you would be decomposing.
Yeah, I'll show you what the design matrix looks like. It's going to look different from what we saw before. Okay, and lastly, we put this all into a big bucket, data set containing all of the different beta maps for all of these different conditions, called MVPA.block.NII. So, if we run this tcsh, just type 1 and then tab to expand that. If you press enter, it runs pretty quickly. Again, not a whole lot of voxels, not a whole lot of conditions, so it does pretty well. By the way, just a little bit of trivia. This voxel loop that you see, it goes 0 through 9, 0 through 9. Each one of those numbers appears, it means that 2% of the voxels have been processed. There's 50 numbers total, and when it gets through all of them, you're done. In case you're curious.
For each one of those 0 to 9.
Yeah, so it's like we've done 3D deconvolvement 2%, now 4%, 6% until we move it all. Okay, no errors. That ran fine with everybody. Awesome. All right. Now, as we did before, because a lot of these commands are going to be very similar, a lot of the processing is very similar, let's take a look at what's in that MVPA block data set by typing 3dinfo-verb and then MVPA.block MVPA.block.NII. You're going to get a ton of output. Don't panic. All right. So this looks a little bit different. It looks familiar, but there is definitely something different about this. Now, notice. Okay, the very first subbrick, that's the full F-stat. We've seen that before. But now we have 1, 2, 3, 4, 5, 6, 7, 8 subbricks of cars. So somebody in their own words tell me what they think that those 8 subbricks correspond to.
Average betas for each subject across each trial.
Close. Yeah, so it's for each trial. Yeah. That's the IM difference. So and you see that for faces and everything else here.
Suppose that the first condition of the card was baby stimulus?
Yeah, so there were 8 presentations of the car stimulus. And we have a separate estimate of what the beta map looks like across the entire brain for that trial. Yeah. So if these, these first 7 car beta maps, if they all look really similar, okay, let's say like their patterns look really similar, that gives us a very, very, that would make the classifier pretty reliable, right? And then if we give it the last one, and it also has a pretty similar pattern to what came before, the odds are very high it's going to correctly classify that. If there's a lot of variability in the beta maps, it's going to be more difficult to construct a reliable classifier.
And this is just for one subject.
This is just for one subject, yeah. Okay, so we have that for all the different conditions. Yeah.
Sorry, you would have conditions multiplied by runs, those many subjects.
Conditions multiplied by trials.
By trials, right?
Yeah. However many trials you have across all of your runs. I think in this case, they had 8 runs of data and they had 1 instance of each condition within each run. So, if you look within the 1D files, let me see if I can pull one of those up.
4 runs.
is a 4?
of A, so
32
equal.
Okay. That makes sense. Where's my stimuli? Let's say shoes block onsets. In any case, there are 8 separate instances of that particular condition. If you take a look at the design matrix, this is something pretty neat to look at. There's a command called AIV, the AFNI image viewer, which you can use to visualize this xmat.1d file. This is your design matrix that's output from any of your analyses, and it's always useful to check. So MVPA.xmat.1d.
What file did you open?
I opened MVPA.xmat.1d. All right, so this looks different from what we saw before, but there are some similarities. Notice we have 8 runs, 1, 2, 3, 4, 5, 6, 7, 8. We've modeled the drift for each of those. And notice, okay, we only had 4, we have 4 separate conditions, but it seems like we have a lot of regressors, right? Specifically, we have 32 regressors, task regressors. So we're 8 instances of cars, 8 instances of faces, houses, and shoes. So each one of those is getting a separate beta estimate. Right? Okay, we can close out of that. Now the next step is to actually extract the betas, and we're going to concatenate them into separate data sets that we can use for the classifier. Take a look at this. Let me tell you a couple more tricks with this. So, you can run your classifier a couple different ways. The way I'm going to do it is running it, training on the even number data sets and then testing on the odd numbered ones. I'm doing the same thing for all the different categories. Let's just focus on houses for now. So I want to create a data set called houses train.nai, and from that statistical data set, I know that subregs 17 to 24 have my beta maps for houses. In parentheses, so this is called a subbrick selector. 17.24 means look at everything from subbricks 17 to 24, but go in steps of 2. So it's going to grab 17, 19, 21, 23. Right? Put those into a house training data set. For the house test data set, from 18 to 24, stepping by 2, it's going to be 18, 20, 22, 24. Makes sense? Very abstract. I'm hoping that this is starting to click. Is anybody completely lost about how this works? It's okay if you are. I just want to make sure that this is solid. Okay. So we have 8 total. We use 4 for training, 4 for testing. I can do cross-validation. That's fine too, but this is a pretty simple example, so it's only going to be even and odd for each of those. So type TCSH2, then expand it with tab, and press enter. Ignore the warnings. Yeah, just ignore them. Not going to go over why it gives you that. If you type ls, you'll see a few new things here. You'll see the training and the testing data set for houses, for faces, for cars, and for shoes. Good so far? Yes. Now step 3, this is a pretty short one, but an important one. this is going to concatenate all of the training data sets and all the test data sets into a separate train block and a separate test block. The reason I'm putting all of them into, why am I combining all the houses, shoes, cars, and faces? Because there are 4 different categories, I want to make sure they can distinguish between all of them. Right? So if they really are separable, or if at least one of them is more separable than the others, I should be able to pick it up. Let's see. So again, TCSH3 _ create train test. And that should run without any problems. Okay, this last step is actually training and then testing the classifier. A lot quicker actually than you'd think it would be. But something that we need to do beforehand, which has already been created, is this train labels.1d file. Okay. Now, pencil and paper are your friend. You need to know which of these numbers corresponds to what. By default, AFNI is going to concatenate things alphabetically. So within my training data set, everything I concatenated together, the first 4 volumes are going to be, I want to say cat, but there's no cats. What was it? Cars. Cars. First 4 are going to be cars. Second 4 are going to be faces. Third 4 are going to be houses, and the last 4 are going to be shoes. Shoes, yes. I'm getting loopy, man. Just give me a second. It's been a long day.
If you haven't concatenated all of the training from the different categories, then technically if you ran SVM on it, wouldn't you just be like training on house and testing for house?
Sorry, run that by me one more time.
So if you didn't concatenate, so the step 2, I think,
Yeah.
where it concatenated all of the data values for across the categories.
Yeah.
If you didn't do that, then would you be just training on house and just testing house? So it wouldn't have like.
It wouldn't have anything to discriminate against.
Yeah.
In that case, I guess the only question you'd be answering is, how reliably can it, distinguish a house from a house, as opposed to something else.
You can do like house, not house.
You could, I mean.
But I feel if you only tested
Yeah.
on a house, or only trained on a house, then what is it decomposing into? Never mind. That's okay.
It's just
I
asking,
kind of see what
testing a house.
Yeah.
This test item is.
Yeah, it's like, was this, I'm trying to think how that would work. I see what you're saying. I haven't done a paradigm like that, so I can't tell you. Usually you want to discriminate between at least 2
Yeah.
categories. Yeah. I mean, there has to be something that it has to be able to classify it as either house or something else. And if it doesn't have something else to classify, how does it determine what the threshold is?
Yeah.
Right? I'm trying to imagine what that would look like, and I'm coming up with blanks. Yeah. Is there like an experimental
No,
design you're thinking about? Okay. Okay, so that's the train labels file. This very last step is going to train it by using this concatenated train block as a train volume. We input the train labels into the train label flag. We output a model data set, and then also restrict everything to a mask.
So you could do this on whole brain or ROIs, right?
You could, yeah. For 3D SVM, it makes a lot more sense to do it in an ROI.
Okay.
Because if you have way too many voxels, you're going to be trying to fit to a lot of noise.
Yeah.
And my guess is your classification is going to be done. Searchlight is different, but we're not going to do Same thing for test vol. So after that's all been trained, we then use the test block as what the classifier has not had any training on yet. Okay. We use the model, which represents the weights of each of these different voxels. Class out means to just give it a binary. Is it 1, 2, 3, or 4? And then what do we call the predictions for? Basically, what do we call the output? We want to call it exemplar. Before we run step 4, notice we're using this mask, which is final.mask.nii. If you want to, you can look at this within AFNI. Let's see here. Oh, by the way, this data has not been normalized. We're looking at a single subject, so we can't overlay this mask on a template. So what I would do is, I forget if this data set has an anatomical data set. Whatever, I'll just use one of these runs that has some spatial information. And then overlay is going to be final.mask.nii. I don't know necessarily how they created this. It seems to be like the entire inferior area of the brain. That's interesting. Okay, I wouldn't have done that, but that's what they gave you. I'd probably restrict this more to the underside right here. But in any case, okay, it's most of the bottom of the brain. Presumably, there are some voxels in there that do some work at discriminating between the classes. So if you're ready, TCSH 4, run SVM, and then hit return. Very quick, very quick. Yeah. Now you get a lot of output, but the thing you're going to want to look at the most is exemplar overall underscore DAG.
It's MVPA.
What's that?
That you run? No, 4.
4, yeah.
No, the letter, or the number. Not the word. Yeah.
Okay, so what you're going to see here, remember our train labels, right? It was 1, 1, 1, 1, 2, 2, 2, 2, 3, 3, 3, 4, 4, 4, 4. In this case, so the first 4 numbers, how well did it do? Chance, yeah. It got one of the test car volumes right, but none of the other ones. For the second 4 numbers, which would be faces, how did it do? Pretty good, yeah. So 3 out of the 4 were correctly classified on the test data sets. For houses, again, pretty good. Got 3 out of 4. And for, what was that, shoes? Yeah, it was okay. We'll see about that. If you wanted to do this systematically, which may take too long today, we would do that, leave one out to try to really determine how accurate it was and how that compared to chance. But just based on this first pass in this demo data set, it seems like faces and houses seem to be best classified within the voxels in that mask.
So just to be
Yeah.
all of ours look slightly different. That's okay.
Yeah. So it is a slightly random process in how it determines what the hyperpoint is. So you may see something slightly different, but I'm guessing that most people had pretty good accuracy for faces.
Yeah.
Right? Did anybody have really bad accuracy for faces? Like 50% or less? Okay. Sorry, what? Yeah, so the second group of 4 should be mostly 2s. Okay, well, out of 30 people. Yeah, it's okay. It's okay. Okay. Believe it or not, this is all there is to SVM MVPA analysis. We've used this to train a classifier, to test a classifier, and you can use this to then create an accuracy distribution, or basically do a test for whether those voxels within that mask are significantly better than chance at classifying one category versus another.
I could look this up on the help page, but you're literally right in front of me, so I'm just gonna ask, can you mess with the algorithm? Algorithm.
I don't think so. There are options you can change.
Okay.
There are options you can change. But what do you mean? But what do you mean by mess with the algorithm?
Well, change parameters.
Okay. Oh, you know what? See, I'm a square, so I never. I'm gonna have to look at this actually. Yeah. Oh, wait, you already said you were looking at the help page. So, like parameter C in the sigmoid polykernel, I have no idea what the hell that means. So I don't mess with it. I assume that their defaults are good. In the vast majority of cases, you know, who am I, really?
If I was gonna change the Q, what would I change?
Yeah, if I were gonna change the key, it's like, you know, I know what like x times x means, kind of. It's probably an exponential thing.
What do I want to change that tube width to?
Go crazy.
Tube.
Oh.
Go wild.
Wide tube. Okay.
You want a wide tube? All right. Yeah, get a wide tube. I'm gonna do something crazy. You ready?
Love it.
Okay. Let's see here. Gotta remove something first. Remove exemplar model. All right, so what I'm going to do, I am going to switch test vol to train block. Is there anyone here committed to stopping me from doing that? Yeah? Why? What's the problem with that? We just talked about something very similar an hour ago. Why is that biased?
Yeah, you're training testing the same time.
Training testing on the same day. Very good. You're ahead of the curve because a lot of people still do this. I know it's cheating, but whatever. You gotta live a little. Okay. Any guesses as to what my classification accuracy is going to look? Okay.
It's not quite cheating.
Okay.
It's just like you would just get overfitting data.
Right. Yes. It's true. It's actually okay. It's a good guess that it's going to be perfect. It's actually not going to be 100% all the time. There's going to be a little bit of variability because the hyperplane.
So there's gonna be one that's wrong.
Yeah, I'm kind of talking out of my rear end, but it's not going to be 100% all the time, as you'll see. But it's going to be pretty close.
Do people do this?
Only by mistake.
Apparently, because people do need to. Okay. So actually, for group 1 is 50%, but for faces, 100%,
No.
houses, and shoes.
It literally called all of my shoes faces.
It called like shoes.
Yeah, the first time.
Okay. All right. Okay.
So I have a question. If we were
Yeah.
actually doing this with a single subject, we would do it iteratively, right? So
Yeah.
we'd train on blocks 1 through 7, leave block 8 out
Yes.
for testing, and then train on blocks 2
Yeah.
through 8 and leave block 1.
Exactly. Yeah.
So then do you average the accuracy for all blocks and then?
Mm-hmm. And take
and
some
then
kind of
cross
standard
subjects
deviation.
to-
Yeah. Good. All right.
So quick question: if you do like other methodology, not to involve like jackknife replacement,
Yeah.
that you include one at a time, it's not cheating anymore, right? Although you're using similar. I mean, like,
No.
well,
I don't know enough about jackknife algorithms to say. How's it different from cross-validation?
Well, just you run the you train the data and test it.
Yeah.
But every time that you're doing that, you basically remove one data set from the entire data set.
Mhm.
You get the average across all of them.
Okay.
Yeah, you just basically another sort of going around that, but
If I'm understanding you right, I think that's okay. Like, isn't that
I mean it's in statistics
Cross-validation?
it's being used, but I'm not
Okay.
sure about fMRI data. So
I don't know. I can't speak to that. In any case, there's no option to do that algorithm in SVM. I really just want to take a few minutes just to decompress, if you don't mind. This is all there is to SVM, I swear. The next thing we're going to do is kind of start to finish. Probably not going to do a group analysis, but a single subject with Haxby. The pre-processing, creating the training labels, and then training and testing it. Everybody okay with that? That may take, I don't know, hour and a half, basically till the end of the day.
I don't want to overwhelm you. Can I ask one question?
Yeah, please.
So understanding that this is the process for like a single subject.
Yeah.
Where in the entirety of the pipeline does the leave one out subject happen? Leave one subject out.
Oh, right. Not okay. So at the single subject level, it would be leave one run out, right? If you're trying to get an estimate of what the average accuracy is for the classifier.
Right.
So that's the cross-validation approach I was referring to. I don't think you would do that at the group level. Basically, you could just take the average accuracy across the subjects that you used cross-validation to get the estimate for, and then test whether that's significant.
Okay, so there's no point within the analysis that we're doing currently where we would do leave one out subject.
Not currently, no.
Got it. Okay.
Yeah. Good question. Yeah.
And also the deconvolve that you run it on all subjects, right? Just the training, you leave one out. Right. Just
Yeah, you run deconvolve on all your pre-processed blocks. You generate one beta per trial, per condition,
Okay.
right?
Oh, yeah.
Yeah. So as many beta estimates as there are onsets in all your onset files.
And
When
when
you
you do
average those across subjects.
Yeah.
And then train and test on those averages.
No, you wouldn't be doing training and testing at that point. What it would look like is something like I can pull up, not that one. One of these. Yeah, so something like this where they're showing, I forget which of these they extracted from, which of these ROIs, but you're basically saying, okay, within all of V1, which I've defined as this right here, this is what the accuracy looks like.
Across participants.
Yeah, right. So this isn't like a whole brain accuracy map, I don't think. I think this is showing some other kind of effect, but they're showing where the different subregions are located. So what we're doing with 3D SVM, we're not creating a whole brain accuracy map, right? You're just saying, okay, I would point out which of the voxels that I use for my analysis, for my MVPA classification, and then say within those voxels, do this entire pattern of voxels is classifying things at this accuracy level. If you wanted to make a claim about the strength of the classification of a single voxel, you do something with the Searchlight algorithm, which would then produce a group level, or sorry, a whole brain accuracy map. Does that make sense? It sounds like a small distinction, but it's kind of a big one because I can only say something about the pattern within that ROI is a significant classifier. Yeah? Okay. Okay, give me 5 minutes, please.